Hi, this is Brian from AutoShopTeacher.com and on YouTube as Brian D. Wampler. Please click on that and subscribe if you would. Today's topic, we're going to be looking at the ASE A6 test series for automobile technicians, and we're going to be going through the practice test questions that are on the current ASE study guide. I'm recording this right now. It's July of 2024. I believe this study guide was published in 2023, so it's somewhere around a year or less old. So let me change the presenter view here and let's get into this. First, a little bit about the ASE A6 exam. You can see there's a total of 50 questions that are scored, but you're actually going to be answering 60 questions when you take this exam with ASE. And that's because ASE adds 10 questions that they're using to test the quality of the question. So, for instance, if somebody takes the test and gets, let's just say, all 50 of the actual questions right, but those test questions, those ones that they're sampling in there, maybe that same person taking that test doesn't get as many of those right, then they go back to the drawing board with those questions and start working them over, and they keep testing the test questions, if that makes any sense, until those questions become a part of future tests. So don't freak out when you see that you have 60 questions that you need to answer. You only need to get the 50 that they're scoring correct, but unfortunately you don't know which 10 questions in that test are not actually a part of it. So just answer every question. As we go through this, I'm going to talk about some of the techniques you can use as you look at each question. We'll talk about the different types of questions. I believe there's 5 different ways the ASE words questions now. But do make a note, again, 60 questions, and the A6 test is the only one that gives you an hour and a half to take. So as far as the standard A1 through A8 test, the A6 is the longest test, and you have an hour and a half. So simple math, if you have 60 questions and an hour and a half, you have about a minute and a half for each question. I'm not going to sit here and demonstrate a whole minute and a half of time, but if you take your stopwatch or your phone or whatever and just sit and run a minute and a half of time, it actually is quite a bit for a single question. So some questions that you get very quickly, take that first gut answer that you have after you've read the whole question and read all of the options for the answers. Take that and mark that as your answer. If you have a little bit of concern, maybe a second thought, go ahead and mark that, down on your scratch paper or whatever when you're taking that test. And then when you get to the end, then maybe go back to those questions. Because then the questions that maybe you have a little bit harder time with, then you can maybe have a little bit more than a minute and a half with each of those. All right, let's look here at the different categories that are in this A6 test. You can see there's 13 questions, so over 25% of the questions are going to be just general electrical and electronic system diagnosis. So a very important part of the test. Then battery and starting systems, charging systems, lighting systems, instrument cluster and driver information systems, and then body electrical systems. And again, 50 questions that will be scored, but you're going to have 60 questions that you have to answer. So let's start with, from the study guide, this is the first question that they list in there. And let's just kind of go through these and see what we can figure out and talk about them as we go through. This probably will be a longer video. If you've watched any of the others that I've uploaded to YouTube and shared on Facebook, this one's probably going to be a longer one. If you're a little weak on electricity in terms of like Ohm's law and the flow of electricity, you might want to watch the video that I uploaded about circuits and Ohm's law, and then come back and watch this video. It might be helpful to watch them in that order. Okay, so here we have the question, and they're saying they've given us a wiring diagram, and the question posed is, in the charging system shown with the engine running, the digital multimeter will display. Okay, so I think my next slide here zooms in on this a little bit better. And let me also change the screen view so you can get a good look at that diagram. Okay, so we see we have a DMM. ASE likes to call digital volt ohm meters. Most of us, I think, say DVOM these days. They're still using the DMM. Okay, so if you hear DMM, it's the same as saying digital multimeter, or DVOM if in your other studies you're used to calling it a digital volt ohm meter. Regardless, you can see that the unit of measurement is volts. So we could even say in this case it's a voltmeter. And we see that one lead is hooked to the positive side of the battery, and the other side is hooked over here to a terminal on the alternator. So let's read the question, read all four answers, and then start figuring out how we would put together our choice for what we would select on this question. In the charging system shown with the engine running, the digital multimeter will display A. Charging output voltage, B. Regulator operating voltage, charging circuit voltage drop, or the last option, ignition switch voltage drop. Okay, what do you think? We see where that meter is connected here between the battery, positive, and a terminal on the alternator. Let's figure out what these terminals on this alternator are doing. Well, we can see this one here is going to ground. Whenever we see that kind of upside down beehive, or whatever you want to call it, but the three lines that are decreasing in length, that means that that's an attachment point to ground. So like a body or chassis type ground, or a ground on the engine. Let's follow this wire over here. From the battery positive terminal comes over. Looks like we have a junction point, and then it comes down through here. Whenever you see a loop like this where a wire, that's showing that those are not connected. Okay, that means that those wires are just passing over. Okay, so this is not a junction point. Up here though, with the dot, we see that as a junction point. So this wire from the battery positive comes to here and branches off, then again branches off here. But we're trying to see what it's doing to the alternator. So it comes down here and it connects, it connects to the terminal that we are currently have our voltmeter attached to. Okay, let's look at this one here. Where's it going? It's coming over here. Oh, okay, it's the one getting power from the ignition switch, most likely when the ignition is turned on. Let's look at this last one. This last one over here is coming around over here. Oh, it's also connected to the battery. Okay, so what would we be testing here? Okay, well, charging circuit voltage drop. Okay, the charging circuit voltage drop. And why am I saying that's what we're testing here? Because we have the lead from the voltmeter attached to the positive side of the battery. We have the other side of the meter attached to the other end of the same circuit. So our voltmeter would show a voltage drop if there was any loss in voltage between this terminal and this terminal. Then that's what would be displayed on our voltmeter. Okay, as far as option A, charging output voltage, well, we would need to have this lead from the meter attached to ground or to the negative side of the battery, so that's why A is incorrect. Regulator operating voltage, we're not even close to connected for testing that. And ignition switch voltage drop, well, we would be testing from where it's connected here on the battery, but this lead would be tested, we'd follow this circuit over, and this lead would be attached to this terminal here instead of the terminal that's illustrated. Let's look at question 2 now. The oil pressure light stays on whenever the engine is running. The oil pressure has been checked and it's at specification. Alright, so we know the engine has proper oil pressure when the engine is running, but the oil pressure light stays on. Alright, let's think about this. Here we have a Tech A, Tech B type of question. Obviously, the last one was a simple, basic multiple choice. We were asked a question, we had 4 possible answers. This one here, whenever you get these A, B, there are 2 questions. Remember, 2 questions that you're having to answer. Then once you have both answers, you can then make your choice. Okay? I highly recommend you just read Tech A's statement, and maybe it's helpful for you to think of them as a person rather than Tech A. So possibly think of Adam, if you like, or another name that starts with A that makes it more relatable, as if you're having a conversation with this technician. And then likewise with Tech B. If you've watched my other videos, I sometimes call him Bob, Tech Bob. But just read Tech A's statement and answer it. Then once you have that answer, focus on B. Reading both of them back and forth and back and forth, it's easy to get mixed up in terms of who's saying what. And therefore, as a test taker, it's very easy to come up with a wrong answer because you mixed up some of what Bob said with some of what Adam said, and you were misled. If you will, that would be kind of one of the tricks that test makers do to kind of trip us up. So, starting with just Tech A's statement. Technician A says that a ground in the circuit between the indicator light and the pressure switch could be the cause. Okay, if you're not familiar with, or if you haven't trained or studied or worked with your just typical oil pressure light, right? This is not an oil pressure gauge. This is just what some people used to call idiot lights, right? They come on, it's a red light, and it comes on once oil pressure has already dropped to a dangerous level. So we're not dealing with a very sophisticated type system. This would definitely be the type of system on a much older vehicle, most likely from the 80s or earlier. So if you're not familiar with it though, let's look at a basic diagram of an old-fashioned, old school, if you will, warning light in the dash, right? So we have a bulb over here, and then we have an oil pressure switch. And we call it a switch because remember, switches are closed or open. Closed or open. Sending unit might have a variable resistance to it, but when we're talking about switches, open or closed. So let's just follow over here from starting over here at the battery. Okay, we know that this is ground. Okay, and they got carried away there with their ground symbol. Today's day and age, again, it's just the 3 lines, but there's an old-fashioned ground symbol for you. So the battery, this side is ground, so we know we're dealing with the positive side over here, and it's traveling through the ignition switch and continuing on through and over here to this light bulb housing and connecting. We know we have a bulb in here, and then on this side, well, if we're going to make the bulb light up, then this side needs ground to light. So this wire here, that's going over the hill and through the woods and connected to this oil pressure switch, if this switch grounds this wire, then this light bulb is going to come on. I hope you're following through this. I used this illustration rather than an actual line diagram to maybe help you be able to visualize what we're talking about with this question. So this oil pressure switch is going to be screwed into the engine. So it's going to be screwed into a ground point. The whole engine is grounded. And you can see here there's this spring inside. And when the oil pressure comes up through this passage, it lifts these contacts off of one another so that they're not touching. Okay, so enough oil pressure keeps this from being grounded, and enough oil pressure then keeps the light bulb from coming on, the oil pressure warning light, because there's no path to ground. Okay, so let's go back here and look at this question, what Tech A is saying. Technician A says that the ground in the circuit between the indicator light and the pressure switch could be the cause. Okay, and again, what is our symptom? The oil pressure light stays on. Okay, so let me show you that diagram one more time. I'll even make it bigger on your screen. Tech A is saying that this wire being grounded in the circuit between the indicator light and the pressure switch could be the cause. So make your selection now on whether or not you think Tech A is right or wrong. Kind of lock that in. Now let's talk about Tech B. Technician B says that an open in the pressure switch could be the cause. Who is right? Let me back up to that diagram. Okay. And again, Tech B says an open in the pressure switch could be the cause. So he's saying if this switch is an open circuit, meaning it has poor contacts, the contacts do not work. Okay, that's what we mean by an open. Again, closed circuit, open circuit. Tech B is saying that an open in the pressure switch could be the cause. All right, you had your answer for A, and now you have your answer for B. Which one is it? Is A right? Is Tech B right? Are they both right? Or are neither of them right? Okay, Tech A is right because the ground turns the light on. And if Tech B is saying that an open in the pressure switch could be the cause, he's terribly wrong because, again, back to that diagram, this circuit's not going to get grounded, so this light bulb's never going to come on. So Tech A is correct. Again, just to reiterate it, Tech A, Tech B type questions are two questions, and make sure you pick your answers individually with what they're saying and then join those together to decide what the correct answer is. All right, this one's a little bit different. Okay, it's not giving us a wiring diagram, and we're going to be talking about power windows though. So let's just read through this question, and then I have some illustrations that I'm going to show you to try and help dial this in for you. So the question states, the passenger side power window operates properly when using the passenger side control switch, but the window will operate in the down position only when using the driver's side master control switch. Which of these could be the cause? So before we get into reading through our possible answers, let's make sure we understand what the question is stating. We're talking about the passenger side window operates properly when using the passenger side switch. So the passenger's sitting there, reaches over, switch up, switch down, window goes down. But the window will only go down when using the driver's side master control switch. Which of these could be the cause? Alright, so now we got it. The window works on the passenger side, but when the driver tries to operate the passenger side window, it'll only go down and won't go back up. Alright, here's our four choices. So this is a traditional multiple choice answer. A pinched wire from the passenger side control switch to the window motor. Now think about that. Option A is saying a pinched wire from the passenger window switch to the passenger window motor is causing this problem. B, an open wire to the driver's side window motor. Where did that come from? Okay, we're not even dealing with the driver's side window motor in this question that's asked up here. C, a grounded power wire to the power window circuit breaker. Okay, think about that one. D, an open circuit in the driver's side master control switch. All right, again, this is a little bit different because we don't have a wiring diagram to look at, but based on your training and experience, I'm hoping you have an answer already. But if you don't, I'm still going to go through this, or I am going to go through this and kind of talk through this. I'm not trying to teach you just to pass the test. A part of this lesson, and for recording this today, is yes, to go through these practice questions, but to also explain why we arrived at a certain answer. And so remember, we're all on different levels in this business, and so that's why we kind of have to, come in at a level where we can all come up to the same point in our training and our knowledge. So here's a wiring diagram. I believe I pulled this up for about I think it was like an 85 Ford Mustang or something like that. And this is a good example of, again, another old school type way that wiring was done for power window motors. In today's day and age, we're largely controlling windows and most accessories with networking. But here is a traditional basic example of a power window system for two front windows that didn't involve a computer and just switches, wiring, and motor. Okay, and let me make this a little bit bigger on your screen. So here's our passenger window motor. And remember, we're saying that it works fine with the passenger control switch, but it only goes down when you use the master control switch, right? The one on the driver's door is the master because it has at least two switches on it, right? The one for the driver's window, but also the passenger window. So we call that the master control switch. Here we see the source of ground is coming and going to both sides of the switch to control the driver's window, but also the passenger window. Okay, but we know that the switch here for the on the passenger door works, and the window works just fine. Okay, but it doesn't work when this switch over here is operated. It'll go down, but it won't go up. All right, let me advance the slide here. And hopefully you've come up with your answer, that an open circuit in the driver's side master control switch is the only logical selection out of the four given. But let's look at the three other answers. A pinched wire from the passenger side control switch to the motor. So pinched wire from the passenger switch to the window motor. Let me back up to the diagram. It's saying that one of these two wires here between the switch and the motor are pinched to ground. But yet the question told us in the original statement that this window works from this switch and the motor works. So that's why we eliminated option A. B, an open wire to the driver's side window motor. Well, I kind of already let that one out of the bag that couldn't be right because it's talking about the driver's side and we're testing the passenger side. And then C, hopefully you picked up on right away just when reading it, a grounded power wire to the power window circuit breaker. Well, that would cause the circuit breaker to trip, right, to go open, and then there would be no power to any of the power window system, either the switches or motors or anything, because it's saying that the power circuit is grounded. So that's why C definitely could not be the option. Here we go, question number 4. This one we have a diagram. Let me make it a little bit larger while we start out looking at this question. The brake lights are not working on the vehicle with the circuit shown. When the brake pedal is with the brake pedal pressed, the technician observes the digital multimeter readings shown. Which of these could be the cause? Okay. First off, the ASE has certain wording that they like to use. And so when they're saying brake pedal pressed, if you maybe been around a little bit, or maybe your English second language, whatever, I just wanted to point out that the English language can be a little bit tricky when it comes to wording of technical questions. For instance, with the brake pedal pressed, what they're meaning in most technical manuals they would actually call depressed. Depressed meaning that it's moved fully from its rest position, it's fully applied. Okay, so brake pedal pressed means maybe another way of saying it, that the brake pedal is fully depressed. Okay, meaning foot on the brake, brakes are applied, applying full pressure to it. Okay, so again, depressed or applied. And again, just also as a reminder, DMM is their digital multimeter, which is also known as a DVOM, or just multimeter. Okay, so let's look at our choices here and see what we can come up with. Or yeah, and I forgot I have one more box up here. All readings are volts. Okay, so all of the digital multimeters are reading in voltage, meaning they're indicating volts. None of them are amps, and none of them are reading ohms. So we got to look at that, and then we also got to look at where are each of the leads for the meters connected. Okay, so let me make this big again so hopefully you can see it. So we have a meter hooked here to right after the fuse. When we see this wavy line, and then 10A tells us that that's a 10 amp fuse, so it's coming from the battery positive through a 10 amp fuse. This meter is reading 12.6 volts. It's measuring between a ground point and the fuse. This next meter is connected to each side of the brake switch, and it's reading 12.6 volts. Then here, well, it's just saying it's a Y. Here's our other meter. Is connected here to the circuit that's running to both the brake light bulbs, and it's connected, measuring from that circuit to ground, and there's no voltage displayed. So again, the brake lights are not working on the vehicle with the circuit shown. The brake pedal is applied. The technician observes the voltage reading shown. Which of these could be the cause? Our options are high resistance at this point in the circuit here, so high resistance. Option B is an open at circuit X. Option C is a short to ground at Y. And option D is an open circuit at Z, meaning this ground point for the circuit is open. It's been disconnected, or it's corroded, or broken off, whatever it might be. Okay. Did you come up with B for the answer? I hope so, because the brake switch is faulty. Let me see if I have another slide. No. Let me talk about this a little bit more. And we'll just go through like we did with the last question, and how did we eliminate the other answers? Okay. Option A, right? Answer A, high resistance at W. Well, if we had high resistance here in this wire, then we would have a different reading on this voltmeter. It would be maybe 9 volts, okay? Because we already see we have 12.6 volts at the fuse. And I'd like to also mention that we have 12.6 because that's actually a 12-volt car battery. When it's fully charged, it's not 12 volts, it's 12.6 volts. Just a lot of times in training we use 12 volts to explain things because it's much easier to do the math of Ohm's law and other calculations. But in the real world, if you're just measuring the voltage of a battery and there's no load on that battery, or it's completely disconnected from the vehicle, it's not fully charged unless it has 12.6 volts in it when it's at rest. All right, option C, answer C, a short to ground at Y. And based on this information, why would we say that's incorrect? Okay, a short to ground at Y. Well, let's see, this one here is 0 volts, so I guess that could possibly be. And then this one here, well, if this is grounded and this has power, well, wait a minute, that could be short to ground at Y. And then, wait a minute, over here though, we have 12.6 volts and it's right after a fuse. And remember, the brake switch is in the closed position, right, because the brake pedal is applied. So if this was shorted to ground here at Y, then wouldn't this fuse be blown and there would not be voltage being measured here? Because if this was shorted to ground, it would have popped this 10 amp fuse. Okay, so that's why answer C is not correct, is because if it was shorted to ground here, as soon as you applied the brake pedal, it would have popped this fuse. And then an open at circuit Z. Why is that not right? So if there was no ground here, okay, meaning this is just open, then how would this meter be reading 12.6 volts? Because the negative lead of this voltmeter is hooked to this wire, and if there's no path to ground, then it would be reading 0 volts on the meter. That's why we got to answer B is the correct one. The brake switch is faulty. Question number 5. Technician A says that if a fusible link in the alternator charging circuit is replaced with a system-sized wire, the circuit will be unprotected. Technician B says that a fusible link in the alternator charging circuit is replaced with a system-sized wire, the battery will overcharge. Okay, I told you to always answer these A and B's individually, but I went ahead and read them both because they're both talking about fusible link. Okay, in fact, the first, what is that, 10 words of the question, of the two statements are exactly the same, other than one says A and one says B. Technician A says that of a fusible link. Technician B says that of a fusible link. This is what I'm talking about, where you got to answer each question individually and not mix up what A and B are saying about things. So again, we'll just start with A. Technician A says that if a fusible link in the alternator charging circuit is replaced with a system-sized wire, the circuit will be unprotected. This is another instance where ASE test for A6 is testing you, or is questioning you about a type of circuit that was used a lot, let's say from maybe up into the 2000s, but really 90s and earlier. Talking cars from the 90s, 80s, 70s, 60s had fuse links, fusible link wire. Vehicles still today have the equivalent of a fusible link, but we usually call them maxi fuses, and they're either replaceable in line, or maybe they're mounted, with hardware and inside of a junction box. But we used to use fusible link wire. And basically a fuse link wire was at the end of a regular wire, and it provided a protection for a circuit. So if this circuit became overloaded, the wire inside the insulation here would actually melt and open the circuit. I think I have another. Here's an actual image of one. You can see it's been pulled off of a terminal here. This is just a red wire. But if you look very closely, let me make the image a little larger. Right here, fusible. And I believe this one also says. So we have at least one. I can't read the green wire in the middle very well. But you can see this is a fusible link. And if that gets overheated, meaning from too much amperage, too much current, the rate of flow through this wire gets too great for what it's rated, it will go open circuit. Okay? So, let me back up there. I accidentally gave the answer. I don't know if you caught that on your screen. So Tech A is saying that if a fusible link in the alternator charging circuit is replaced with a system-sized wire, the circuit will be unprotected. So what that question is stating, or to give you the information if you're not familiar with fusible links, is they're saying that that fusible link had failed, and Tech A is saying that if you go in there and you cut that off the end of the wire and you just solder in another piece of wire that's the same size, notice it says the same size, but it's regular wire, it's not fuse link, then the circuit will be unprotected. So does that sound correct to you? Now let's look at Tech B statement. Same thing. Tech B says that the fusible link in the alternator charging circuit is replaced with a system-sized system-sized wire, the battery will overcharge. So Tech B is saying that if you replace this wire, just like Tech A said, if you replace this wire, but Tech B is saying if you replace it with regular wire, then it's going to cause the alternator to overcharge. Okay, fuse link is just it doesn't have resistance built into it. It's designed to melt when excessive current flows through it, but it doesn't add resistance to a circuit. So therefore, if this wire burns and you replace it with a regular wire, well, Tech A is the only one that's going to be right. You've now restored connection, but you didn't use fuse link, you used regular wire. Okay, so yeah, it's probably going to work, but you just left that circuit unprotected. So if something happens in that alternator that causes it to short, or if the alternator maybe has a short in it already and you just eliminated the fuse link, when you connect everything back up again, good chance you're going to melt the whole wire from end to end and any other wires that are alongside of it. Tech B, I think, just doesn't know what fusible link is, and was maybe assuming that there is resistance in fuse link, and so if you remove it and replace with regular wire, then somehow that would cause an overcharging. I'm not really sure. But in this case, you've now seen a couple of pictures about fusible link, and you've heard me ramble on about it, so if you encounter this sort of question, you're a little bit better informed, hopefully. Alright, there's a total of 9 questions on this practice exam. We're up to question 6 now. A starter solenoid clicks, but the starter does not crank the engine. Technician A says that a burned solenoid contacts could be the cause. So what do we think? A starter solenoid clicks, but the starter does not crank the engine. Burned solenoid contacts could be the cause. Let's keep that in mind. I'm going to go ahead and read Tech B statement. It says that the poor battery cable connection could be the cause. So, starter solenoid clicks, but the starter does not turn over the engine. One tech is saying solenoid contacts, The other one is saying poor battery cable connection. Let's look at a couple of things here. I had to go back to, I think it was about 95 in the wiring diagrams to find just a simple basic starter motor with a solenoid on it, and then cut and pasted it in here so we could kind of get just a very basic old school look at a wiring diagram for a starter and solenoid that doesn't involve any other circuits. So the battery here is connected to the right front of the engine on the negative side. The positive side battery has a wire running over here and to this starter motor. Okay, or more accurately, I should say the solenoid on the starter motor, because this is the actual motor part, the electric motor part of the starter. This part here is illustrating the solenoid. I didn't want to bring in the whole giant wiring diagram, so I can tell you that this other lead off of the battery is going up to the ignition switch and then to the neutral safety switch, and when the ignition switch is turned to the start position, then it applies power to this purple wire. Okay, let's back up a second. Tech A is saying that burned solenoid contacts could be the reason that the solenoid clicks, but the engine does not crank over. Technician B says that a poor battery cable connection could be the cause. Alright, back to our diagram. Tech A is saying burned contacts. Well, if you're not familiar with how a solenoid works, they have two windings inside of them, and one is to pull the core of that solenoid in and engage. So you can see right now it's in the non-applied position, and when you generate a magnetic field, with the one coil is going to pull it in and the other one is going to hold it applied until the power on this purple wire is released at the switch. So Tech A is saying that burned contacts in here, right, when this solenoid gets applied and this part of the solenoid swings over to here to make contact with the wire coming from the battery, that a poor contact, burned solenoid contacts, could be the cause. Okay? I think A has a valid point. Let's look at Tech B again. That poor battery cable connection could be the cause. Well, we can see over here at the battery, we have the one wire that's going off to the rest to power the rest of the vehicle, and then it makes its way through when the ignition switch is turned to crank position and puts power here. But Tech B is saying that this wire here, again, poor battery cable connection could be the cause, saying that if this wire, battery cable, has a poor connection, it could cause the solenoid to still click, but the starter motor to not get power. Okay? Well, if this wire were not even here, or very poor connection, well, we still have this other wire over here that's going through all of those switches and ignition switch and neutral safety switch and applying power here. And the starter motor itself, the whole starter and solenoid, is grounded, so we would still have a complete circuit for the solenoid part, for the contacts to move. But if we didn't have power here on this wire, then it still would not make the conduit circuit connect all the way and cause the starter motor to turn over. I hope you're following me on all this. All right, here we go. So Tech A is correct, and so is Tech B. It could be the contacts, and it also could be the cable. Question 7. The horns in the circuit shown operate only when a jumper wire is connected between terminals 30 and 87 of the relay. So terminal 30 and terminal 87, if you grab a jumper wire and you hook it between here and here, then the horns will sound. So the horns each have individual grounds and they both receive power on the same circuit. So one thing we can derive just from the very first part of this question is that we know the horns and the grounds for the horn are good, because if we take power here from this circuit breaker and jump it around the relay to the power supply of the horns work. So we just confirmed that this whole part of the circuit and the horns themselves and the grounds are good by jumping that. So let's see what Tech A, or Adam, has to say about this. Technician A says that a failed horn relay could be the cause. Okay, what do you think? If this relay is bad, would it possibly cause the horns to not work? Let's think about that and then kind of lock that down as your answer for whether or not Tech A is correct. And now let's look at what Bob, Technician B, has to say. That a short to ground in the circuit between the horn relay and the horn could be the cause. Okay, short to ground in the circuit between the horn relay and the horn. So Technician B is saying that a short in this wire between the relay and the horn relay and the switch. There we go. See, you gotta be careful. Horn relay and horn switch, right? I almost sidetracked myself right there. So you gotta make sure what you're studying or what you're trying to answer about. Well, let's see here. We have power coming in here. One side goes to the 30, the other side goes to the 85. We see we have a magnetic coil inside here. So then if we ground this circuit, that's what causes the relay to engage and closes these contacts. So again, Bob is saying that if this wire here is shorted to ground, that could cause the horns to not work. Well, the purpose of the horn switch, when it's applied, is to connect this wire to ground. So I'm going to just go ahead and talk about Bob here for a minute. If this wire were grounded all the time and the relay is good, then the horns would be sounding continuously. Let's go back to A. You should have your answer already for whether or not Tech A is correct. Technician A says that a failed horn relay could be the cause, because if you jumper around the relay, the horns work. Well, Tech A, I think, has a valid point. It's maybe not the only possible scenario, but it is saying that a could be the cause. Yeah, there's a few other things that could be the cause. Tech A is the correct answer. It's not shorted, right? Tech B is saying that if this wire is shorted, well then if you jumper it across from 30 to 87, the circuit breaker is immediately going to overload and go open circuit. So Tech A is the only one that is correct. Alright, question 8. Which of these digital multimeter, or again, DVOM readings indicates a current flow of 3 amps in a circuit? So this one's not even asking you about a car. This question is seeing if you know units of measurement that are commonly used in the automotive industry. So let's talk about it a little bit. Okay, it's asking you if you're reading a digital multimeter and in what it's going to say on the meter to indicate 3 amps. So I think we can eliminate the bottom one immediately, option D, because if it was indicating 3 amps, why would it say 0.3 amps? Because, right, amps, they're both saying amps, so 0.3 is not the same as 3. So we can eliminate answer D. But options A, B, and C, you can only pick one of those 3 if you know the terms micro and milli. Because you can see Answer A is 300 microamps. Answer B is 3.0 milliamps. And answer C, 3,000 milliamps. So we can kind of eliminate B even if we don't know what a milliamp is, because 3.0 is the same as saying 3, right? It just has the point and 0 after it, but 3 is the same as 3.0. So we can kind of eliminate B just doing, logical thinking. But let's talk about what a microamp is and a milliamp is. And just for side reference, this also applies to measurement of time, right? We have seconds, but then we also have microseconds and milliseconds. So let's talk about milli first, the one here on the bottom. Milli, whenever you see that in a measurement, it means 1,000 or 1,000. Okay? Micro, which if you're just starting out in your training, you're probably not going to be dealing with for a while. But just so you know, it's a million. Okay? You've probably heard of a micron, or like air filters rated in, or oil filters rated in microns, and how large of a micron they'll let through. That's basically saying particles that are around 1/1,000,000th in terms of size. Okay. Getting back on track here, we're talking about microamps and milliamps, and we're trying to figure out if a DVOM or multimeter is saying 3 amps, how it could possibly be displayed. So we have 3 amps, and if we take 3 amps times 1,000, then that would be indicating 3,000 milliamps. So it looks like answer C is our conclusion. Okay, C is correct. 3 times 1,000 is 3,000. For our last question, one of the 5 types of questions or formats of questions ASE uses is the reverse question, if you will. It's giving you, it adds the word except, which means if you misread this question, you're going to go through and think that there's 3 right answers. But it's asking you the except, which means find the wrong answer. I know that sounds backwards and upside down, and that's pretty much exactly why they word some of the questions this way on the ASE exams, is because they're trying to make sure you're paying attention. Because as you start reading through one of these types of questions, but you haven't adjusted your mind to thinking that it's an except type question, you could get really thrown off track and grab what you think is a right answer out of the 4, when actually, if you're looking at the question incorrectly, well, there should be 3 right answers here, but you're looking for the except, so you're looking for the wrong answer. Anyways, here we go. Question 9. Any of these could cause a high starter current draw except. So again, we're trying to find what one of these answers would not cause a high current draw. Okay? When you see the term current draw, you can also think of it as current as amperage, right? And amperage is, again, the rate or flow of electricity. If you haven't watched my intro to circuits and Ohm's law video, I highly recommend you do that if you're not familiar with volts, amps, and ohms and what they measure and how they relate to the flow of electricity. So again, current is amperage. So this question is saying any of these could cause the starter to draw an excessive amount of current or amperage, except for one. So we need to find the one of these choices that would not cause a high starter current draw. Okay? I've yacked on for a little bit here, hopefully long enough where you've read through the answers. I'm going to read through the answers and then start moving to wrapping this up and getting you the answer. So, starting with A, worn starter bushings. Well, A, worn starter bushings could cause the starter motor to bind and draw more amperage. So we just eliminated A because it could. We're looking for the except, and answer A could cause what we're talking about. Answer C, grounded field coils could provide a path to ground and increased amperage flow. Again, if you're not familiar with Ohm's law and the flow of electricity, please check out that other video. C, grounded field coils could provide a path to ground and increased amperage flow. And then D, a seized AC compressor could cause the engine to be harder to turn over and increase the amount of amperage the starter draws. Right? AC compressor driven by a belt. Belt is hooked to what? The crankshaft pulley. If the AC compressor is seized and you're trying to turn over the engine with the starter, it's how having to slip that belt around the crankshaft pulley or the pulley on the AC compressor that is going to definitely make the engine harder to turn over and cause the starter to draw more amperage. So B is correct. Relay is not very likely to cause excessive current draw when starting an engine. I hope all of this has been helpful for you. I am available for one-on-one coaching and training, and I invite you to give me a call or check out autoshopteacher.com or go on YouTube to Brian D. Wampler. Please subscribe and watch the free videos I've put there. I'm also available for custom group sessions. I also teach at a private technical school for emission control students and ASE preparation. And then I also coach and mentor shop owners as well as service advisors. I have nearly 40 years in the automotive service industry, and I'd love to hear from you, and I thank you for watching.